Now, the idea of a cyclic universe is certainly not, the concept of a cyclic universe is certainly not new. It's pretty ancient. It goes back in the East to Heraclitus and the early Stoic philosophers. In the East. I mean, in the West, there's Heraclitus and the early Stoic pre-Socratic philosophers. That's what I meant to say. Or in Eastern philosophy, Hinduism, there's a very complex cyclic universe, very detailed cyclic version of the universe. So the idea of a cyclic universe has been out there along with the idea of a created universe or the idea of a static universe. There's always been these kind of three competing ideas out there. And in modern cosmology, it's also not the first time people have discussed this idea. Shortly after general relativity was invented, the first thing that Einstein invented was a static universe. When Hubble discovered that the universe was expanding, couldn't be static, that idea had to be ditched. Two other ideas were born. One is the one we know as the Big Bang universe, the created universe, and the other was a cyclic universe. And people like Lemaitre, who was one of the fathers of the Big Bang model, and Einstein, who was the father of general relativity and the static model, themselves thought about this idea of a cyclic universe. They called it an oscillatory universe. And it was the idea you, again, probably learned in school of a universe which is expanding and stretching, expanding and stretching, expanding and stretching. So if there was enough matter in the universe whose self-gravity is enough to overcome the expansion of the universe, the universe would kind of breathe. It would expand to a certain point. The matter would cause it to recollapse to a point, and then it could bounce and happen over and over again. So it would produce a universe that looks something. If you were looking at the size of the universe, we would sort of graph its size, and it would look something like this bouncing universe that we're showing over here. Now, this idea has been abandoned and is dead several times over by the present time for various reasons. The first reason why it was killed was sort of theoretical argument posed by this fellow. He was trained as a chemist but became a cosmologist. His name is Richard Tolman. And although he liked the idea of a cyclic idea, he saw that it would violate a fundamental law of thermodynamics, which is the second law, the famous second law, which says that entropy is always growing in the universe. So if you try to make a cyclic universe which is like this, well, what's actually happening between, what does this represent, this little bumps here? Well, they represent the universe expanding, creating stars and galaxies, and then recollapsing again. Well, when you create stars and galaxies, they're irreversible processes that increase the entropy or the amount of radiation or the number of degrees of freedom in the universe. And when you bring the universe back together again, you have all the entropy that existed from previous cycles, but now whatever new stuff you just added. So when you come back and bring things back together again and collapse it, you have not the same entropy you had the cycle before, not the same amount of radiation or temperature you had before. You have additional stuff from what you just created. And that'll get more additional stuff the next time, more additional stuff the next time. And that additional stuff affects how you bounce. You don't bounce the same way if you have more concentration of entropy. You actually change the bounces so they go like this instead. They actually get longer and longer and longer going forward in time. So the fact that you're reconcentrating is a problem. They go more and more forward in time. Going forwards in time, that's not a problem. You just get longer and longer and longer. But your goal was to try to get rid of this idea of a beginning of universe. And that you failed to do, because going back in time, they converged to zero size in a finite time. So you thought you got rid of the idea of a beginning of time, but actually all you did is you pushed it back a few bounces. So this was disappointing to people like Einstein, who were motivated to think about, didn't like the idea of the Big Bang being a beginning and were looking for an alternative. This said the alternative failed. Now nowadays we would say this model also fails because it required that there be enough matter to close the universe, to cause it to come back again. And we've now measured the amount of matter in the universe, and it's not enough. Not enough by at least a factor of 3, more like a factor of 4. Furthermore, we know the expansion of the universe isn't slowing down. It's actually speeding up. So it's the opposite of what this theory predicts. So this theory cannot be saved. This theory is dead. So if we're going to talk about a cyclic universe, it's going to have to be a new kind of cyclic universe. And it's going to have to use some new ideas that get around these problems. So, in terms of outline form, it's going to be a universe which has a bang. I haven't called it a big bang. It's not quite as big a bang in the sense that the big bang, when we say it, usually means a point of infinite temperature and density. This bang will have a large, very large temperature and density, but it will be finite. So it'll be, a billion times hotter than the sun, but not infinitely hot at its hottest. We'll go from the bang. We'll immediately have expansion and cooling, the formations of stars and galaxies. But we don't have any inflation. So we still have to explain why the universe is smooth and flat, but it won't be through inflation. The idea is to avoid inflation altogether. So it's really a very big alternative in this sense. We'll have dark energy. We need to have dark energy to explain the observations, but actually you also need it for this theory. It plays a key role in the theory. If you try to make a universe which is cyclic, let's think about the universe for a moment. In the original Big Bang picture, you begin with this hot fireball that condenses to form stars and galaxies. If you're going to make something cyclic, you somehow have to get back to a simple beginning again. What do you do with all the stars and galaxies you just made? Well, you have to get rid of them. Well, the best way to get rid of them is to stretch them apart from one another and return the universe to vacuum. And dark energy is a very effective way of doing that. It turns the universe almost everywhere to vacuum. Where it doesn't turn the universe to vacuum, those regions might be spoiled. You might not form galaxies there at the next time around. But everywhere else where the universe is vacuum, we're back to a simple, pristine state where we can get back to a simple beginning again. So dark energy isn't just required observation, it's actually required to make this theory work. Then it goes through a period of contraction. It's not going to be contraction quite in the sense that I was describing before. I'll describe it in a moment, but it's a special period of contraction which even turns out to further smooth and flatten the universe. Although not quite so, it'll leave slight inhomogeneities after it's done. Then the universe will crunch and rebound and bounce into a bang, and the process will again over and over again. But the smoothing and flattening does not occur after the bang, just after the bang or inflation. It actually occurs, well, in each cycle, beginning now as the dark energy takes over, and between now and the next Big Bang. So the Big Bang doesn't just happen once, but it happens over and over again. And it's what happens between now and the next crunch that sets up the structure for the universe to come. So it's not just cyclic, but what's happening in one cycle is actually affecting the next cycle, which is affecting the next cycle, et cetera. So it's a very interesting, more intricate more subtle kind of cyclic model than even the ancient ideas one had before. Now, to explain it in yet one more level of detail, well, I have to do one of two things. One is I could introduce some mathematical equations, and I didn't think that was the hour to do that. And the other is to introduce some ideas that will seem strange at first, especially if you're hearing about them for the first time. But then afterwards, if you get a little used to them, I think you'll see it provides a very natural geometric picture of what could be going on here. So the ideas I want to introduce don't come from cosmology, but come from more fundamental physics, attempt to unify fundamental forces with gravity, namely the theory known as string theory, or a version of it known as M theory. So, okay, that's a little jarring. Let me relax you a little bit into it. String theory, what makes us think that's a good idea? Well, what makes us think that's a good idea is that it has a very simple unifying principle to it. We know that in the laboratory observe there are many types of particles that exist in nature. We have a whole catalog of types of particles. In string theory, they can all be understood as all actually being the very same entity, a vibrating string. If you had a super microscope, they could have looked down to scales of 10 to the minus 30 centimeters. You would see that what you thought was a point particle was really a little piece of vibrating string. And what made different particles different from one another was the fact that they were vibrating with different tones. It's a very pretty idea. So just one entity can explain everything that we observe. Every particle we observe can be understood as a vibrating string of one sort or another, including gravity itself. Now, it's a quantum string. That means it's not allowed to vibrate any way you want. There's certain rules, quantum rules about it only vibrates in certain ways, but that's what gives you the discretely different kinds of particles you see. So that's already a beginning idea, powerful idea. In fact, it's the only theory which is a finite theory of quantum gravity we have at the present. It's our best hope of a unifying theory of gravity. Now, to make this idea work, one needs to introduce more than the dimensions we know in our everyday lives. So the point is that to have the string vibrate in all the ways you need to explain the particles you see, you have to assume not just 3 spatial dimensions, but additional spatial dimensions. Now, of course, we only see 3 dimensions. We only experience 3 dimensions. So we have to do something to hide those extra dimensions from If you're going to make the theory consistent with what we observe, we have to do something to hide those extra dimensions. What can we do to hide them? Well, one thing you can do is you can take an extra dimension and you can kind of close it in a circle. So some dimensions can be, think of a soda straw. It has one long dimension and one small dimension. Okay, so if you were a flea walking on the straw, you see it as a two-dimensional straw, but if I show you the straw from a distance, it looks one-dimensional because you can't notice the extra dimension. So it could be that some of the dimensions of space, and that's the basic idea of string theory, are wrapped up, curled up in such a way that you just can't see them. And there are 6 of those dimensions. In M theory, there's yet one other additional dimension that gets hidden in a different way. It gets kind of sandwiched, and that's kind of what I'm trying to show here. So think of, let's ignore those first 6 dimensions. Let's think of our three-dimensional world as being like a three-dimensional world, which I've drawn here as a piece of flat paper, but it should be three-dimensional. And there's an extra dimension, a fourth spatial dimension, which we can't reach out into, along which, on the other side, there's another similar kind of world. Not identical world, but similar in the sense that it has 3 spatial dimensions. Its details, its particles might be different than ours. The space, the extra dimension, only exists between these 2 walls, or membranes, and these are called branes, B-R-A-N-E, or brane worlds. The laws of M theory say that particles that we know happen to have the property that they are stuck like flies on flypaper on just one end. We're allowed to move in 3 dimensions, but we just can't move in the 4th dimension. We're just forbidden. We just don't have that capability of moving in that direction. Similarly, there's particles on the other end that are only capable of moving on that end. But there's space in between, but no space beyond. So the universe, in terms of this extra dimension, is a sandwich. The whole thing is the universe, with our 3 dimensions, which I should really draw them in 3 dimensions, but I'm drawing it kind of this way, and the 4th spatial dimension in between. This theory ends up being able, this version of string theory ends up being able to describe a lot of details that we actually observe in the laboratory about elementary particles. So although it seems kind of bizarre, it actually unifies in a very powerful way lots and lots of different measurements, and that's why people are interested in this idea. Okay. This is also, if this theory is correct, then our theory of cosmology has to be explainable in terms of this picture. So let's think about the Big Bang model explained in terms of this picture. So the Big Bang model says you first have nothing. That's what they're shown there on the left, far left, nothing. And then suddenly you have to have the universe. So the universe would mean you have nothing, and then suddenly there emerge these 2 brane worlds, okay? And they have to merge from the same place, like and then they suddenly, so a quantum fluctuation, they suddenly appear and they move apart. Then they must contain the right kind of inflationary energy to cause them to stretch at this inflating rate. Then this inflationary energy decays. It leaves little wrinkles in them. The wrinkles end up, at least on our side, forming galaxies and stars. We don't know what they form on the other side, etc. So that would be the Big Bang theory expressed in the language of string theory. Now, if you look at that sequence, you might come to invent an alternative picture that would fit almost as well, which is, why not that? Why not, instead of the universe suddenly beginning from nothing, it's almost inviting you to say, well, actually that picture over here, that's what I call the Big Bang, might not be the beginning. It might be that these 2 brane worlds existed before, collided, and then bounced apart again. So what would that look like? It would look like a collision of 2 objects. And when 2 things collide, they heat each other up. They'd fill it with matter and radiation. And then once they come apart again, they'd begin to expand. It would look just like a Big Bang. So it leads you to the idea. Once you see this idea, you can see geometrically there's 2 possibilities. You began from nothing, or a Big Bang as a collision. But that's a big difference. Because a collision means something exists before as well as during as well as after. So the Big Bang, instead of being beginning, there now exists a prehistory to the Bang. And as far as we can tell, we can't tell which of these pictures is correct from anything we know from string theory at the present time. They're both logical possibilities. But the second possibility is very interesting because once you have that idea once, well, why would they collide? Well, they could collide because they were thrown at one another, although who does the throwing? More likely they would be colliding because there's a weak force, kind of spring-like force that's drawing them together. But if there's a weak spring-like force that's drawing them together, why should they only collide once? They could do it again and again and again. And so so you're pretty much led pretty soon led to a picture of the universe which looks something like this little cartoon. So this doesn't represent everything in the theory. The timing isn't right, but it represents conceptually what we're talking about. A collision. It heats the universe with hot matter and radiation. Once the hot matter and radiation is produced, it causes the universe to stretch, just like in the Big Bang picture. The universe becomes interesting. My computer broke this morning, so I'm having to use this as backup, which is not quite behaving the way I'd hoped it would. That's interesting. It behaved differently this time. Let's see if it continues to go. It's going to shut itself off again. If it is, I'll try a different, I'll just say something a little bit different. Spread itself out again. Oh, it did. Okay. Well, okay. What the movie was supposed to show is that it happened again and again and again. Okay. So you could have to imagine that it happens again and again and again. So, in fact, what happens in this theory is that a spring-like force has with it, associated with it, an energy. Just like if I have a spring and I stretch it, there's energy stored in the spring. That energy acts just like dark energy. So when the branes are apart and stretched, there's dark energy there held in that spring-like force. There's also matter and radiation. At first, the matter and radiation is much more abundant and much stronger than this energy, much greater in energy than it. So the spring just remains stretched. But when the universe expands enough, like at the present time, then this energy begins to dominate the universe, causing the stretching of the branes to accelerate and become emptier and emptier, which is just what we're seeing now. But it doesn't last forever because it's associated with this force which is trying to bring them together. And as it brings them together, the spring is going to unwind. And as it does so, the energy has to be released. It's being converted from potential energy to kinetic energy, just like in an ordinary spring. So in this picture, the dark energy can't last forever because it's created by the force that's trying to draw these two worlds together. So what happens is it gets converted to kinetic energy, which when they collide gets converted partially into matter and radiation, which then gives us the matter and radiation we need to start the cycle again. And then the spring-like force can continue with the help of gravity, can continue to do this process forever, cyclically. Whether it's literally forever or many, many times or exponentially many times, we don't know. There's no limit, no physical limit to how long it can go that we know of. But these cycles could be going at least for a very, very long time. And during this process of contraction, during this process of contraction, the universe gets smoother and smoother and flatter, except, so now I'll have you look at the thing again. I'm sorry, I can't keep it going. Notice, so this is supposed to represent the moment in the future after the universe has become empty, and there's almost only these flat, if you like, worlds next to one another. This is really flat. And now what happens as they move towards one another is you might notice the picture represents the fact that they wrinkle up. So once they stop stretching because the dark energy the spring begins to unwind, what happens is quantum fluctuations will begin to take over, just like they did in inflation. And what the quantum fluctuations do is they cause the branes to wrinkle. And because it causes them to wrinkle, when they hit into one another, they actually don't hit each other at exactly the same place, same time everywhere. They're not hitting like that. They actually are hitting slightly unevenly. So when they come apart again, different regions have bounced before other regions. So different regions are hotter than other regions afterwards because they bounce later and heated up later than other regions. So you can now compute on the back of the envelope, again, like we did for inflation, what do we expect the distribution of radiation to look like after this collision? And the answer is that. It looks almost exactly like inflation and exactly like we observe. Even though the physics is completely different than inflation, for completely different reasons, it produces almost exactly the same outcome. To the level we've measured, indistinguishable. So that's really interesting. Inflation, decaying, uneven bang produce the same outcome. Can produce the same outcome. Yes?
We have a theory of the age of the universe.
Yes.
Is there an interval in the theory between the two planes colliding?
Yes, we can calculate all those things. So when we say we have a theory of the age of the universe, what we really have, now we have to rethink it, we have a theory of how long it's been since the last bang.
Right.
So if there's many bangs, all it's telling us is we're 14 billion years since the last bang. It tells us nothing about what existed beforehand. So if you figure for reasons, various reasons, we estimate that the lifetime of the cyclist is roughly 1 trillion years, plus or minus a factor of 10 or something like that, or a few factors of 10, but 1 trillion, that would be a typical number. Then we're sort of early on into one cycle. Yeah, and then it turns out this phase of contraction itself lasts roughly 10 billion years. So it's very, very slow. Inflation was very fast. The whole thing lasted 10 to the minus 30 seconds. This is ultra slow. It lasts about 10 billion years. Yes, in the back?
What happens to all of the matter at the end of the cycle when the brains come back together?
Good, good. That's a very important question because we said there was this problem in the original cyclic models, the old oscillatory models, that you had this entropy problem, which is related to the fact that the matter and entropy were all being brought together. So again, I'm sorry the movie didn't keep going, but the idea is that during the phases of expansion, the brains are stretching and they're emptying out. And all the matter and radiation that was produced from previous cycles, that was produced in the previous cycle is being diluted. The universe becomes almost empty vacuum anywhere. The contraction, though, remember, is not a contraction along our 3 dimensions. It's a contraction along the extra dimension. So we're taking explicit advantage of this idea of extra dimension to say the contraction that's important here is the contraction of that extra dimension. So when the 2 brains come together, the diluted matter and radiation entropy is already still diluted. There's no reconcentration of it. So you have the same situation of 2 empty brains colliding before as you did a cycle ago. So the result is the same. There's no reason why the cycles should be, to within small uncertainties, exactly the same. Now, if you think about that a bit, that means that this is not really, in some sense, a cyclic model. As to say, if I'm following the volume of the brains, they're constantly growing. More and more entropy is being produced from cycle to cycle. However, we, as observers, don't observe the entire universe. We only observe a patch of it. So the kinds of things we're able to measure are things like the temperature, the density of galaxies, the density of black holes. Those will all be the same. Okay? The number of black holes, the amount of matter will be different if you could see everything. But since we only get to see a finite part of it, to us, locally, it seems like things are cyclic. So it seems cyclic, even though in actuality it's not quite cyclic. Yeah?
Is there any evidence that rather than the Big Bang, this is just a Big Bang and there are other bangs?
Out there?
Is there any evidence?
Well, the first thing we want to know is...
Just one bang?
Yeah, so you're getting ahead of the game. We first of all just want to ask the question, when we look at that picture, that globe of the microwave background radiation, the first question you want to ask is, was that created after the bang, or was that created before the bang? And now, once I know that question, then your second question becomes meaningful, which is, how would I know there existed yet an earlier bang or a future bang? But first of all, we want to answer this first question. We haven't even answered the first question yet, observationally. The answer is, obviously, we haven't answered the question yet. We don't have evidence yet. Yes, Rocky?
Our third graders would ask the question, stretching into what?
The answer is not stretching. I mean, stretching is stretching. You can create more stuff by stretching it. So best way I can answer that question is to say, imagine you begin with an infinite rubber sheet, okay, and you line it like graph paper, okay. So there's little squares. It's broken up into little squares. And now imagine I stretch it such that each square grows by a factor of 2. Now I'd ask the question, where has it stretched into? Doesn't have any meaning. It's just intrinsic. It's just stretching, right? And if I ask, well, there was an infinite amount of space before. How much is there now? Infinite. Okay. So the answer is that those kinds of global questions, if you like, actually don't begin to make sense in this context. It makes sense to say, what's the density of things? Things have spread out. You can talk about that. But you can't, and you can talk about space being created. There's more space in some sense than there was before. That's where the space that made up, that's why the squares are bigger. But it doesn't make sense to ask what about the totality. Yes?
The short form of my question is so what?
So what?
What's the significance about which theory?
Oh, huge. Okay, so I think huge, but let me save that question for just a bit. Let me just talk about one other issue first. which is how we might distinguish these theories, which I think you might want to know. I promised you that this isn't just metaphysical discussion, but we actually can do measurements that will decide which of these theories is correct. So let me hit that, and then we'll come back to your question. So as I said, the two theories agree with everything we observe up to the present time about galaxies, about microwave radiation, etc. But if we were to make finer scale measurements, especially about this radiation in the early universe, that was formed in the early universe, it turns out we could distinguish these two theories. That's where they begin to break apart in their predictions. In particular, one important one has to do with the existence of what are called gravitational waves. Gravitational waves not produced by the collisions of black holes, where you've probably heard about them, but produced by inflation itself, or produced by the collisions between these branes themselves. And these gravitational waves are ripples in space-time that, if they were to move past you, would kind of squeeze you in one direction and stretch you another, and then the next moment squeeze you in that direction and stretch you in the other. They'd have this shearing effect as they move past you. That's what the space does to them. They're extraordinarily weak, but they're not so strong enough that they would leave, if they were powerful enough, they could leave an imprint on the microwave background. They leave a certain pattern in the microwave background radiation. In particular, they would cause the background radiation to become polarized. And this is kind of a cartoon to represent looking with Polaroid lenses at the microwave background of this radiation from the early universe. You would find they would leave a certain polarization pattern of radiation if they were there in the sky. Now, an inflationary model predicts that there should be strong gravitational waves. The cyclic model, this collision between branes, has the property that it produces almost zero-strength gravitational waves. So one of the key things you want to do is check whether these gravitational waves exist, which is to say, check whether or not the characteristic polarization pattern you would expect to exist in the microwave background is there or not. So if you were to look at the sky with this radiation from the early universe with polarized glasses, they should produce a kind of swirling pattern of radiation, okay, that we should be detectable. That's what we're looking for. So there are experiments in space, called the Planck experiment in space, which I think I have a picture here, of the Planck satellite experiment, which was launched last year and which is beginning to make measurements now, which is looking to see if it can, with polarized detectors, detect whether there's this gravitational wave imprint there or not. If it sees it, then the cyclic ideas are dead because they can't produce that kind of effect. And if they don't see it, then that adds support to the cyclic picture. It kind of points us in that direction. So this is an example of a key test. There's a second test which I won't describe, but there's two different tests we can do, and this is one of them. So we don't have to wait around forever to decide which is correct, because between the Planck satellite and experiments being built on the ground, on mountaintops, and being launched by a balloon in Antarctica, we hope to really learn the answer in just the next few years. But in the meantime, we're sort of caught in between. We don't know which one is correct. So let me just return to your question and say, what's the difference between these two ideas? Why do we care about these two different ideas? Well, of course, one reason is, well, we're interested in the history of the universe, and we want to learn something, and because which of these theories is correct tells us something about what happened in the Big Bang and the fundamental physics of gravity and the nature of quantum gravity, whether the Big Bang is necessarily a beginning or not. But more generally, just stepping back, you might say we're kind of just debating between two different views of the nature of time. Is time having a beginning and sort of go linearly forward? Or is time effectively cyclic? I mean, things exactly repeat, but in some sense, average properties of the universe repeat, and the universe, and so if the average properties of the universe are repeating over and over again. That's really what we're contrasting. And what we've seen from this talk, I think, is that if in this linear theory of the universe, we end up with a universe with a number of interesting properties. First of all, in such a theory, because of this period of inflation that occurs at the beginning, it wipes out all information about what existed before inflation. Our vision is in a certain sense limited. By limited, I mean if you want to know what happened to the Big Bang, you've lost all that information. It all got inflated away. So we're not able to answer directly, observationally, or experimentally anything about what happened at the Big Bang. The future is in a certain sense bleak. The universe in this picture is accelerating away and will become an empty wasteland within 1 trillion years and just continue to be more of that in the future. The universe has this structure in which it's inherently random, and where we are can't be argued to be typical. It's in some sense atypical, and its properties are entirely random, not under control, not predictable. And you might contrast that with the alternative theory we've developed, which has the property that, well, your vision extends beyond the Big Bang. What you're looking at when you see the same microwave background image, this is that same globe just stretched out here on this oval. When you're seeing this microwave background image in this interpretation, you're seeing the Big Bang itself. You're seeing the splats produced by the bang itself, and the rip, and the fact that it wasn't particularly even is owing to effects that occurred before the bang. So you're actually able to study the bang and even study what happened before the bang, what the conditions were like leading up to it. So a completely different physical interpretation. The future is hopeful, if you regard it as hopeful, in the sense that the patch of space where we are now won't be is not evolving into an eternal wasteland. It's going to expand for a while. It's going to empty out, but then there'll be new matter and radiation created. In a cycle from now, there'll be, new galaxies and stars created. So it isn't wasteful. I mean, the inflationary picture and dark energy picture is, in some sense, very wasteful. You produce a lot of space, which is completely useless in terms of making stars and galaxies. Here, it's, if you like, very much more efficient. And every bit of space is used over and over again, so it's economical in this sense. In the inflationary picture, you have this eternal runaway, and so different patches of the universe can end up you produce an infinite number of patches, and you end up producing patches with an infinite number of possibilities. In the cyclic picture, you don't have this runaway picture at all. The universe sort of keeps itself more or less in sync, and every bit of the universe that collides ends up producing stars and galaxies and having the same physics as we observe. So you end up producing a universe which is the properties we observe should be the properties you would see anywhere in the universe. So we are able to learn something about the universe as a whole, and the laws of physics are, in some sense, and the physical properties are universal, truly universal. So there's two very different outlooks on the universe, two different implications for fundamental physics in terms of what happens at physics at the Big Bang, but we don't know at the present time which is correct. So over the next 2 years, all of us will have fun thinking about these two different possibilities and debating them and deciding which ones you like better. But which one you like better doesn't really count. Nature gets to decide which one is the winner, and we'll find the answer to that in a few years as well. Yes?
I have just a basic question. Has the Big Bang in any way ever really been proven? If so, where did something appear from nothing? How is that ever?
So that question, did the Big Bang happen and things like that, is something that really bothers astronomers and astrophysicists and like, because when we ask that question, we're often mean two different things. Okay, so I just want to be careful before I answer your question. I know which one you meant, but I just want to be careful to distinguish them first. There's first of all the idea that the universe was once hot and has been expanding and cooling, and space is stretching. For that, we have overwhelming evidence that it's true, and we actually have enough overwhelming evidence to describe it in full detail with full observational evidence beginning from 1 second all the way up to the present. So that idea is definitely the case. And that is what, when many astrophysicists and astronomers say the Big Bang theory, that's what they mean. Now, if you pin them and ask the question, does that mean you're confident from your observations or whatever reason that the Big Bang was a beginning? Most of them will say, well, that's a common view, but we don't know it to be true. We have no proof to be true because, in fact, what's happening is we're extrapolating to points where we can't observationally test, using a theory which at a certain point we know can't be properly extrapolated too far back, because if you go too far back, we know quantum effects become important, and Einstein, when he developed his general theory, didn't know about didn't include quantum physics. So we know the theory we're extrapolating isn't correct. And we don't yet have a replacement, an improved theory of gravity yet. I ascribed the one which is the leading alternative, and it's not even developed enough to tell us for sure what happened. So the answer is we don't know. That part is not proven. So we don't have the idea of beginning from nothing to something. Now, you could ask the question, is it, based on laws of physics we present low, conceivable that that could happen? Do we have even the inklings of mathematics that would explain how that would happen? The answer is yes. People have developed that idea of so-called quantum cosmology, where you could have sort of sort of a decay from no space and matter and radiation to suddenly something. You can go from nothing to something. It's related to what I was telling you about gravity before. You might think, see, normally we think you can't go from nothing to something because it doesn't conserve something. We have some idea in it. But think about what I said before about gravity. Beginning with 0, I can create positive matter and negative gravitational energy. It still sums to 0. But I have something. I have space and matter in it. So there's nothing we know about the laws of physics that forbids us from doing this. It's conceivable that we can do this. It's mathematically conceivable, physically conceivable, based on what we know. Although it's pushing our quantum physics in a domain that we've never seen space created. We've seen, uranium atoms decay or particles decay, but we're using that same object, the same ideas for space. We've never seen it in that case. We've never seen the Big Bang, but we don't know anything that blocks us from doing it. So we're allowed to imagine it. And so part of the important issue, you're asking why it's important, is if we were to prove the inflationary theory correct, well, that would be kind of forcing us to say, well, okay, this beginning idea must somehow be correct. Okay, push us into that corner. Whereas otherwise, you might not be pushed into that corner. You might say, oh, okay, maybe there is something yet to be discovered why that idea doesn't work. So the experiments can help us answer that question. It's kind of interesting that we can measure something, the polarization, and answer something very deep and you would think is far beyond the reach of science, which to answer a question.